Well, it's a tremendous honor to be at this famous workshop. It's actually my first time, although you've been here 10 years, and it's great to be in the heart of energy research. I think many people in Saudi Arabia call themselves the kingdom of energy, but you know, the bulk of the research that drives the industry is here, and it's exciting to be at the fusion of these two high-tech thrusts of the energy industry itself and the high-performance computing industry. That's a view of our campus from the Red Sea. And I'd like to start off the talk with a theme from the hockey great Wayne Gretzky. A good player plays to where the puck is, while a great player plays to where the puck is going to be. And the hope for this talk is that we'll look at algorithms for where architectures are going to be. There are many indications from the traditional semiconductor roadmap about what the sweet spots, or maybe they'll be sour spots actually, but they're the spots where we have to target for future HPC. And such algorithms may or may not be the best today, although they're heading in the right direction. And usually if you target future architectures with more energy austerity, less bandwidth, less transmission, and memory capacity per core, you're going to run better on today's machines as well. So the outline of my talk is to briefly go through some architectural and applications trends that suggest that while we could be quite happy at the petascale, there's sort of a transition where things hit dead ends at the exascale, the next factor of 1,000, and then look at a set of 4 fours in terms of what we can do about this situation. 4 algorithmic imperatives, 4 sets of bad news, good news about these imperatives, 4 widely applicable strategies in re-engineering our algorithms to target the emerging architectures, and then 4 points of light, 4 little examples of work in progress in the Extreme Computing Center at KAUST. And I'll suggest many other frontiers as well, but I'll just show a few slides to give an idea of how these strategies can be applied to diverse areas of the waste of the hourglass, the software, the critical software stack that maps many different applications coming from PDEs and so forth into many different architectures at the bottom. So you can keep track of the 4s. So the architectural trends. Clock rates, as we know, have ceased to increase, but arithmetic capability continues to increase through flooding cores. Memory storage capacity on a per-core basis falls behind the arithmetic capability. It's increasing, but not as fast. Same thing with bandwidth. It's increasing, but not as fast on a per-core basis. And the mean time between hardware interrupts in these increasingly complex systems will shorten, putting perhaps more burden, at least for the most efficient way of computing, on the software rather than exclusively on the hardware, the way we do it today. For example, with error-correcting code in memory, we write and then we read back and we compare. If we didn't need to be 100% sure, we could be 99.999% sure that that memory write was done correctly and that any fault in it could be detected by an algorithm, for instance, a residual popping up or something in the next iteration, or a pixel in a movie that we don't care because the eye is going to correct. If we could take a little bit of the burden off the hardware and put it on the software, that would actually make a big difference in future energy-efficient computing. So in the meantime, billions of your favorite unit of resources of scientific software, a lot of it open source, contributed by academia, the Department of Energy, international science agencies. This all hangs in the balance until our algorithmic infrastructure evolves to span this growing architecture applications gap. Now, for the architecture side of my arguments, I rely heavily upon the International Exascale Software Roadmap, which is a product of the science agencies of the G8 countries. They met for about 5 years, starting around 2006, and published this roadmap in 2011. I think it has not been much invalidated since then. In fact, it's only been really much more validated. And one part of this was looking at architectural trends. And while we obtain the next order of magnitude of performance, roughly, the peak machine in the world today is about 100 petaflops, the Taihu light system in Wuxi, China. That's getting about 5 to 8 gigaflops per watt. The target is to get the next order of magnitude of computing power without another order of magnitude of electrical power. In other words, to go to about 50 gigaflops per watt. And in the brave new world of semiconductor hardware, we won't have the same performance reliability of processors that we're used to. Might be for for heating reasons that the chip self-monitors and cycles on and off or changes the clock. We will typically, because it's easy to engineer a lot of different processing devices and cheaper than the corresponding memory and bandwidth, we'll probably have over-provisioned inhomogeneous nodes, sometimes dark, and switching back and forth between different capacities within the same node. And this required reduction in electrical power per byte and per flop may make computing and moving data less reliable. The circuit elements will be smaller, they'll be subject to greater physical noise, there'll be less space redundancy or time redundancy to have the hardware handle all of the error, and this is something that is a great horizon, I think, for research in numerical analysis and other aspects of application software. If we look at the driving force, it's this growing gap between the energy required to compute and the energy required to move the data. This is a chart from John Shelf of Berkeley showing that the typical double precision floating point multiply add today, C gets, A gets, A plus B times C, is about 100 picojoules. 2 orders of magnitude greater is the cost to move those arguments from a remote place on the system across the network to that CPU. And there's a variety of energy scales in between. Now, a pico doesn't sound like much energy. You guys are used to dealing with, gigajoules of things, not picojoules. But anything you do 10 to the 18th times a second adds up. That gives you a mega, right? So 1 picojoules at an exaflops for the computing alone, never mind moving the data, is 100 megawatts. A megawatt year costs in the US about $1 million. So if we have a 20 megawatt exascale computer, that's a $20 million power bill. We don't want that to be a $200 million power bill. By the way, as OECD citizens, we use continuously about 1.4 kilowatts. So a 100 megawatt computer would be the equivalent of about 71,000 people, a rather expensive device to run. Now, EXA is different. We've heard these threats, about having to change our software for many generations, from mega to giga to tera to peta, and we always seem to have a nice, stable, MPI-based environment where what the system does and what we do, more or less, we maintain those responsibilities. So why is EXA so different? It's not necessarily because Moore's law is ending immediately, but Dennard's MOSFET scaling law has more or less ended. This is from his 1972 paper showing that when you increase the doping by a factor of kappa, you can reduce the device dimension by that same factor, and the voltage and the current and the capacitance elements can all go down. And for the same square centimeter of silicon, you get kappa squared times more computational power. Same power, same area, kappa squared times more power. But copper doesn't work the same way. As you shrink its dimensions, the resistance goes up, and eventually those two curves cross. And we've known this was coming for about 4.5 decades, and now it is unfortunately here. If you read the Top 500 bulletin just 2 days ago, of course, this threat that Moore's law is breaking down is a regular occurrence in headlines in our industry. It's just slowing down. It's not completely breaking down, but companies are not making their original targets for the shrinkage of devices, and we are really heading to a physics-based crossing of the curves. Now, there are many kinds of architectural resources to enlist in the future HPC simulations. The processing cores are increasingly heterogeneous, as you've heard about at this meeting. Memory is increasingly hierarchical: registers, caches, DRAM, flash, stacked memory, partially reconfigurable, like the new Intel KNL, where at boot time you can decide how much of the MCD RAM should be part of cache or part of the flat memory. The internode network is getting to be highly intricate, and of course the internode network as well. So there's a lot of non-uniformities in the structures of these elements. And there are well-established resource trade-offs to balance them against each other. For instance, in the James Demel group at University of California, Berkeley, for several years now they've had a focus on communication reducing algorithms showing that many of these scale-pack implementations of linear algebra and many stencil-based operations, which are equivalent to a sparse matrix vector multiply, have achieved their flop optimality, but not their communication optimality in the standard software. And they've been able to use extra memory. If it was lying around, it wasn't needed to store the problem in order to reduce the communication volume. In a similar spirit, there have been a number of attempts to reduce the synchronization frequency of some of our favorite algorithms like conjugate gradients by doing many matvects at once and then only orthogonalizing in a big block rather than one by one. For instance, the work of Giesels and Van Rooze. There is a trend towards higher order discretizations, which do many more flops per degree of freedom and have, if they're, for instance, discontinuous Galerkin or spectral, they don't incur the large halos that high-order finite difference methods do, for instance, and this really helps boost the arithmetic intensity, the number of flops executed per byte moved. And this is another way of balancing this growing inequity between flops and bytes transferred. And we'll look at a few more of those towards the end of the talk. I would argue, as an algorithms guy, that node-based weak scaling, just adding more fixed processor memory ratio units to a large system is routine if you have performance reliable elements. But the thread-based strong scaling within a node is really the research frontier. So an exascale configuration might be 1,000,000 1,000-way 1 gigahertz nodes. 10 to the 6th, 10 to the 3rd, 10 to the 9th, you get 10 to the 18th from that particular configuration. Expanding the number of nodes up to 1,000,000 would not be a serious threat to many of our favorite algorithms today. Newton's method with a Krylov linear solver with some domain decomposed preconditioner, as long as we have a good way to balance the load precisely and make sure that the nodes are performance reliable. But the real challenge is expanding the number of cores on a node and using them usefully without expanding as fast the memory bandwidth or the memory capacity. And in terms of doctoral dissertations, we don't need to wait for the first exascale systems to work on this part of the frontier. A single node of a GPU or like a MIC from Intel today is a good laboratory for addressing this particular part of the frontier. So this is the familiar. These are a few of the world's top 15 systems, including our system at KAUST'S, Cray XC40, which is currently number 15. The number 1 system, I was just there last week at the G8 Big Data and Extreme Computing Workshop in Wuxi, China. The US's second largest system, a Blue Gene, and of course the K machine in Japan. But those are not the difficult environments. The difficult environments for algorithms are these, the new many-core and multi-core systems and GPUs. Think about 2 decades of evolution from the 1997 ASCII red machine, the world's first terascale system, one on which, by the way, my team at that time, combination of NASA and Argonne and Old Dominion, won a Gordon Bell Prize, first teraflops system. Today, that system is dwarfed by 1 card of an Intel mic. This card actually is 2 or 3 times the power of this system, and it's about 10,000 times more energy efficient. And of course, within that chip, there is a complex network, a very multi-layered memory hierarchy of layers of exclusive and shared cache, vector units, a rich XY network, data at the extremes in MCDRAM or in conventional DRAM. Programming this chip is not so different from programming the original terascale machine, and they're after all at the same scale. Stack them up in a chart like this. The ASCII red produced 1.3 teraflops on nearly a megawatt of power. The Intel Knights Landing, as I say, is about 10,000 times more power efficient, as is the new Pascal from NVIDIA. And both of those power efficiencies are mirrored in the number 1 system in the world today, the Taihu Lite, which, because of the extra burden of all the network and disks and so forth, isn't quite as power efficient as the individual processing element, but it's way up there, 8.3 gigaflops per watt. The exascale system needs about another order of magnitude of improvement in power efficiency. This is the system as envisioned by the US Department of Energy in their exascale computing project roadmap. So let's think for a minute, what do today's simulations look like? They are typically iterative methods based on domain decomposition and message passing. All data structures that scale are distributed. You can't have any data structure that's exclusive to a node. That would be a bottleneck. Each individual processor works on a subdomain of the original. It exchanges information with other processors at regularly synchronized intervals, at boundaries, in parallel, communication parallel as well. And this system, we've been programming this way for about 25 years. We call it bulk synchronous processing, single program, multiple data, communicating sequential processes, a variety of names in computer science. It stems from a paper called that introduced bulk synchronous parallelism by the Turing Award winner Leslie Valiant, who observed that this system has the same favorable property of the original von Neumann architecture. Namely, it's easy for people to compile to this architecture, and it's easy for hardware people to build to it. Now, there is a suboptimality of the bulk synchronous computer and computational environment, which is that we have this very expensive network, which could be a significant fraction of both the acquisition cost and the operational cost of the machine, that we use very sparsely. We want to compute all the time, and every once in a while, everybody gangs onto the network and has a lot of contention, and then we go off and computing it. Maybe that's not already, the most efficient way to use the resources, but it's a great way to program too, and it's a great way to, have the hardware match on at the other end. So, this is domain decomposition. All of you in reservoir and seismic do this. You have a domain where within a domain, whether it's stencils or spectral or whatever, there's a lot of intensive computation and data dependencies, and across the lower dimensional subdomain boundaries, a 2D surface in a 3D domain, we have a portion of communication, which we maintain in constant ratio as we scale the system by adding more processing nodes and more data points. And so we defeat Amdahl's law. We keep the overhead constant as we scale up. And this model has been very successful in reservoirs, in mechanics, materials, magnetohydrodynamics, all kinds of applications. This is as measured, for instance, by the Gordon Bell Prize, which is awarded annually at the Supercomputing Conference. If you track this from its first instance in 1988, where the winning application had delivered about a gigaflops, to a couple of decades later, it's about a factor of 1,000 every 10 years delivered to real applications, tracking very well the HPL benchmark that ranks the top 500. And there's in some years, a Gordon Bell Price Performance Prize is awarded. Here are 3 successive decades where you can find the history of that prize. And just as the performance, if cost is no object, increases by a factor of 1,000 every 10 years, the price, the acquisition cost to deliver a practical gigaflops has been decreasing, not quite by a factor of 1,000, but close to that every 10 years as well. So this is an impressive legacy for bulk synchronous processing. Why would we ever think of getting off of that powerful train? We've had the same model, the same assumptions about who is responsible for what, the same classes of algorithms. And now, unfortunately, if we really do want to get to the exascale, drive down the number of meters per mesh point in a seismic or a reservoir model to get more resolution and presumably greater predictivity, we will be facing this exascale barrier, and I would encourage us to face it with zeal and excitement rather than reluctance and moaning. It is qualitatively different, and it looks more difficult, but remember, those of you who, like me, are old enough, we once said that about message passing. Will developers and users ever really make friends by taking this operating system feature of moving data around into their own programs? And we did it, and we were successful, and we will do it again. There's potentially big gains in colonizing exascale for predictive science and engineering. It's not going to be a distraction for those of us who are in the research side, but an intellectual stimulus, and the journey will be as fun as the destination. Now, unfortunately, there is this bugaboo called synchronicity. Almost all good algorithms in linear algebra, differential equations, integral equations, signal analysis, we like to globally synchronize. And frequently, we do inner products, we do norms, we pivot in linear algebra, we compute fresh residuals at a fixed point in simulation time. These are addictive idioms for efficient algorithms. They already constrain us at about 100,000 processors. They can even make us fragile for smaller concurrency and subject us to the fickleness of algorithmic load imbalance, for example, in mesh refinement or multiphysics, and hardware performance variation, etc. But concurrency is heading into the billions of cores. It's already at 10 million on that Taihu Lite system. So we're at the point of a baton pass from the bulk synchronous generation to the energy-aware generation. So thanks to all the sponsors for fueling all these great PhD theses at Rice, where a lot of the most important advances for HPC have been made for a few decades now, going back to the first NSF Science and Technology Center here on scalable computing. Now, I referred earlier to the International Exascale Software Roadmap, that effort between 2006 and 2011 from the G8 country science agencies. At about the point that that roadmap was published, the emergent convergence of big data and extreme computing was apparent, and so the same group began a new initiative with the support of the same agencies, but more big data people coming in. And that report is not quite in final form, but you can download a draft at the URL above, exascale.org. And from that new effort, I draw my applications constraints. So we've talked about the architectural constraints, now the application constraints. Essentially, they are cultural. These two worlds of big data and extreme simulation rarely converse and rarely address similar applications. Their software stacks are completely different. You go to a big data, a machine learning, a data mining conference, you probably won't know anybody there. They use a completely different, well, yeah, we have Linux at the bottom, but their entire software stack is different from the one that as a simulation person I am used to. But there are many reasons for these two divergent universes to come together. And this single slide may be the most important one of my talk if you're about to go write a proposal on this. This is something that we just worked out a couple of weeks ago at the last week, I guess it was at the Wuxi meeting. So what do these other forms, the third paradigm is simulation, the fourth paradigm is big data. You should think of it as divided into two parts. Analytics, where the algorithms don't change as the data is throughput, and learning, where the data changes the algorithm for the next set of data. These two subcommunities within the big data community don't always talk together either. This one is typified by Spark or Hadoop, and this one by TensorFlow and other of the popular machine learning algorithms. And what do they offer to simulation? Why is it absolutely imperative that these two worlds begin talking together to improve our concerns in simulation? Analytics, real-time in situ analytics, can improve steering through a high-dimensional parameter space to leave out a lot of computation which is less fruitful and to avoid a lot of I/O, which may actually dominate the running time of the application in a PDE simulation where it's time-dependent and where we're sort of going through a large history. Machine learning can also make us more efficient in terms of I/O, in terms of smart data in situ compression, never dealing with the entire data set, but that part of it which is salient for the scientific or engineering purposes. And also, we have a lot of simulations which have empirical functions, climate simulation with cloud albedo, or maybe many constitutives in reservoir modeling. We can actually, instead of supplying those functions as empirical, maybe the system can learn them better, and provide another enhancement to our simulation. Simulation also has benefits to the big data community. The big data community is running blind without the knowledge of the conservation laws that would restrict a lot of useless solutions in their statistical space. But simulation provides, if you will, regularization from the world of physics. And to machine learning, it supplies data for training. And it can augment real-world data where it's hard, actually, to do experiments, but easy to do simulations. And these two sub-areas of big data also have reasons to begin to talk to each other. And I would argue that this is really one of the reasons that this quagmire here, we have to evolve past this, and exascale will, if the real opportunities represented in this chart are to be realized, a big burden will come on the algorithms community. So that's a long-winded introduction from the A of architecture and the A of applications. Let's spend the rest of the time on our algorithms. So here are 4 imperatives that come from the preceding. We need to reduce synchrony, either in frequency or in span. A lot of local synchronization isn't as bad as a lot of global synchronization. We need to reside high on the memory hierarchy with our dominant working sets, so that we are fetching operands with maybe 1 order of magnitude delay instead of up to 3. And we need to increase the programming in a SIMD style, vector type operations, where 1 instruction executes thousands of operations. And we need to perhaps build more resilience into our side of the computational environment. So for each of these, there's sort of a bad news, good news. We have to explicitly control more of the data motion, because this is, as engineers, the highest return. This is where the energy goes. This is where the time of the execution goes. But we'll be given more opportunities to do it. Right now, a lot of those things are hidden from us by the compiler, the operating system. We already control horizontal motion in the sense of message passing. We do a fair amount of vertical now, rolling things in and out of GPU memory, for example. And in the future, there'll be many more tools available to the programmer to map specific data elements to specific areas of memory and not leave them to a random, uninformed control. The default use of uniform high precision in nodal bases on dense grids may decrease to save time, save storage and bandwidth. Nowadays we're lazy. We have a smooth function. It has many degrees of continuity, but we represent it with a series of double precision values on a densely packed mesh. A much more efficient basis could be used. Also, it's continuous in time, not only in space. So we tend to overwrite the full 64-bit values, whereas only maybe the last few bits are changing. That's a lot of memory bandwidth that's being wasted there. We should learn, as we did in the early days of linear algebra, to do iterative correction, compute the correction in the finer bits with single precision and add it on to the state vector in double precision. And we may actually see some of this activity built into the hardware. For instance, in message passing, a network may remember the last time you sent that word from this address to this address, it only differed by the bottom few bits, so let me only send those few bits. And equidistributing errors to minimize resource use will lead to a lot of innovative numerical analysis. Fully deterministic algorithms may come to be regarded as too synchronization vulnerable, not in banking, not in insurance, but maybe in scientific computing, where we expect statistical answers. Rather than waiting for missing data in a network of 1 billion elements, we may be able to predict it. After all, what did I say? The problems have continuous solutions often. Machine learning may be able to predict the next element that's going to be transmitted before it even gets there. And if we're wrong, we can always roll back a little bit. We have a lot of success of predictivity without any models at all. So why should the models be subject to such strict constraints? And again, this will be a rich blending of statistics and classic numerical analysis. Fully hardware reliable executions may be regarded as too costly. We will undoubtedly see a lot of algorithmic-based fault tolerance. Sandia Labs has a major effort in this particular thrust. And I believe that developers will learn to partition their data and their program routines into 2 sets. Those that absolutely must be executed reliably, just like they are today, and those that could usefully and cost-effectively be executed less reliably. For instance, applying the preconditioner. If applying the preconditioner isn't perfectly reliable, it can be detected as a pop-up in the residual and addressed. A single, bit flip that leads to a big spike, if it's a diffusive problem, that's very high frequency. That will dissipate away within another iteration or 2. Whether we can figure this out from the underlying mathematics or some other way, if we can, have a securely executed part and a almost always correctly executed part, we may be able to better engineer these systems for predictive science use. There are many examples in direct and iterative linear algebra already, and we're only returning to the world of the founding of computing. Von Neumann in 1956 actually wrote a paper on cellular automata called The Synthesis of Reliable Organisms from Unreliable Components. So algorithms must, I believe, span the widening gulf between ambitious applications, multiphysics, adaptive, so forth, and austere architectures, long vectors of instructions, less synchronization, more energy efficiency. So the algorithms will have to, span this gap. And this is a full employment program for Rice PhDs and other computational scientists and engineers. So what will exascale algorithms look like? I hope they will still be optimal. We have a large family of algorithms that are order n log n operation count for a data set size of size n. Since nodes on a supercomputer are delivered with a fixed ratio of memory to flops, we have to try to preserve that ratio in the algorithms, or else we will come into an imbalance when we scale up. What are some examples? There was Cooley and Tukey's FFT in the 60s, Hackbush-Brandt multigrid in the 70s, Greengard-Rocklin fast multipole in the 80s, Griebel, Zenger, sparse grids in the 90s. All of these replace one or more powers of n with one or more powers of log n. There are hierarchical matrices, Tertishnikov and Hackbush of the first decade of this century, and then randomized algorithms like Martinson and Rocklin, again, replacing some n's with log n's, or k's, low rank in our most recent decade. And these kind of algorithms must be ported. They do have a lot of hierarchy. They don't match simply onto the uniform, vector-like instruction space of GPUs and PHYs. But with great computational power, as one of my grad students at KAUST said, comes great algorithmic responsibility. This is the required software for the Department of Energy's new exascale computing program. There's model-related software that perhaps most of us who are researchers in the PDE area are used to considering, in our domain. There's development-related software. How do you debug at 1 billion cores? How do you profile to get, ideas of where the power and time is going at 1 billion cores? And then there, of course, is the production-related software, the workflow and interrogation and curation aspects of computing. The high-end computers come with very little of this software. Most of it gets contributed by the user community, and most of it emerges first in the theses of grad students. I have my own little area of interest, and I hope that many others in the room are looking at some of the other pieces. So, a recap of the algorithmic agenda. Reduce synchronization and communication, reside high on the memory hierarchy, greater SIMT style thread concurrency, and algorithmic resilience. Then we want to quantify trades between limited resources and then go address this big fusion of big data and extreme simulation that the exascale is intended to exploit. All the post-forward problems. Once you can solve the PDE without gasping across the finish line, you can solve it many times in optimization, in data assimilation, parameter inversion, uncertainty quantification, and so forth. So let's look at the strategies. One very fruitful strategy that is emerging is to employ dynamic runtime systems based on directed acyclic task graphs, going back to the fundamentals of what is available to be computed rather than over-ordering things in nested loops and over-modularizing things in terms of subroutine boundaries where everything syncs. Now, there are many examples of such systems. Charm++ is a classic one, used a lot in chemistry. There's a large number of experimental systems now. Quark, StarP, Quark is from Tennessee, StarPU is from INRIA, Legion from Stanford, OMPSS from Barcelona, HPX from Indiana, ADLB and Argo from Argonne. These are some of these systems that enable a user to express the computations in a graph and execute as many as are physically available, causally available, I should say, at once. Another strategy is to exploit data sparsity of hierarchical low-rank type. I've heard a few talks about that at this meeting. I'm incredibly impressed how progressive this community is in terms of soaking up the latest results of computational math. But we do need to meet the curse of dimensionality with the blessing of low rank. And then we need to employ more higher order discretizations because they're more memory and memory bandwidth efficient for the same degree of accuracy. And we need to code more to the architecture, but present an abstract API for productive use of the community. Now, a few words about taskification based on DAGS. It may be very familiar to some, but it may be quite new sounding to others. The goal here is to remove artifactual synchronizations and expose more concurrency. It has some disadvantages. You have to manage this task graph, and you potentially would lose some memory locality if you wanted to exploit all the concurrency. So there's a balance between those two. Maybe we should be, build task graphs within a node, but not lead to message passing across nodes, for example. Here's a classic, simple example. This comes from a little 4x4 symmetric eigenvalue problem. So the number of tasks is very small, but this is, for instance, Schrodinger's equation in chemistry, where A and B are matrices representing the Schrodinger operators. What we would do is first do a Cholesky factorization of B in order to apply the factors L and convert the generalized eigenproblem to a special eigenproblem, AX equals lambda X for a new A. And then we would apply, so that carries out that transformation. And then we would apply tridiagonal reduction and finally QR iteration to get the eigenvalues and eigenvectors. Instead of those separate, these are the first three of those routines, sorry. The Potter F, the SysGist, and the SY EVD. We could, in fact, represent the tasks in a way where the critical path, the distance from top to bottom in instruction count is smaller and where the concurrency is wider. And in this graph, the edges are data dependencies, and time is vertically downward, and wide is good, and short is good. And here's an example of a loop being unwound in a complicated GPU-based adaptive optics application where about 10,000 mirrors are being correlated to account for atmospheric turbulence and improve the image of this yet-to-be-built world's largest telescope. And there are several loop bodies in the green and the blue and the diamonds which are actually being executed simultaneously while preserving all the data dependencies between those loops. So here is an example of the way greater concurrency is brought into such an application. This is by my colleague Hatem Eltayev, who spoke yesterday afternoon on a variety of related topics. Now, let's look at hierarchically low-ranked operators. We want to shrink the memory footprints to live higher in the memory hierarchy. Higher means quicker access. We can reduce operation counts by storing and manipulating less data for the same resolution of the math, and tune the work to accuracy requirements. We don't have to go to a full factorization. We could stop early and still have a good preconditioner. You can't do that with Gauss elimination, but you can with hierarchical low rank. The disadvantages, of course, is we have to pay the cost of compression going in and out is non-trivial sometimes, and not all operators compress well, but a surprising variety do, including wave-like operators that emerge in seismic imaging. The key tool is hierarchical matrices. Going back to the observation of Huckbush in 1999, that the off-diagonal blocks of typical operators that arise in mathematical physics have low effective rank. The full operator is full rank, it's invertible, it's well posed, but the off-diagonal blocks could be compressed while preserving the full rank of the overall system. And by exploiting this, we can go to algorithms that are ln-log in the problem size and polynomial in the rank. And whether you win or lose depends on a lot of constants, but increasingly, we're winning. You can have fewer blocks of larger rank or more blocks of smaller rank, depending on the complexity of the data structures you're willing to tolerate. Here's a simple example. This Laplacian operator, this 1D Laplacian, has full rank, of course, but this block can be written as an outer product of two vectors. That's not surprising. It's a sparse matrix to begin with. The fun part is that its dense inverse, this matrix is the inverse of that one, it's fully dense, but each off-diagonal block has exactly the same rank. So instead of storing a very large block here, you could just store two vectors and have all of the data in that block. You could also, if this block has rank greater than 1, maybe represent it by a small number of such vectors. This leads to this kind of a representation of an originally dense full rank operator where you hierarchically subdivide until you find pieces that are representable with small rank and then you keep on subdividing to finer and finer scales until the overall original matrix here is represented by the union of the green low rank and the red full rank remaining blocks. So it's a complicated data structure, but it can be manipulated even on GPUs. We have examples of such software in our own group that are destined for the Hourglass library. Some pieces are already there, more are on the way. This is a way of getting uniform low rank by hierarchical subdivision. This is a way of a simpler data structure where these off-diagonal blocks that are quite large may have to be higher ranked. It's a rich tuning space. Then the idea of employing high-order discretizations. Again, I think I've mentioned this enough, but the disadvantage I haven't mentioned. Namely, some of these higher-order discretizations are less compressible, and they're less amenable to our best algorithms like algebraic multigrid. Okay. So then we need to code to the architecture, and I'm being cued that I'm getting close to my time here, which is unfortunately true. The advantages of coding to the architecture are that by tiling and recursively subdividing, we can create large numbers of small problems that work extremely well in a batched mode on GPUs and mics. They reduce the call overheads, and they give us a polyalgorithmic approach based on block size. We can also take advantage of hardware features like non-temporal stores, where we have something computed in registers and we send it to deep memory without polluting the cache at every level on the way down. Coalesced memory accesses, double buffering, so we're doing communication and computation at the same time. These all reduce sensitivity to the memory bandwidth. The code is more complex, yes. The code is architecture specific at the bottom, yes. But we can present a uniform API at a mid-level for developers. Now, if you're going to address such an agenda, the first question you should ask is Amdahl's question. You know, where's the bottleneck? What's the part of the code that needs to be improved first? And the two main things are linear algebra on dense symmetric matrices. These come up in chemistry and optimization. Sure complements in linear elasticity, covariance matrices, and statistics are all of this flavor. They're all large and dense and growing. And then there's, of course, Poisson solves, usually the highest order operator in many systems of PDEs, and a bottleneck in that it has a global Green's function. So these are some examples that we're working on in our research center. An eigenvalue problem that does, in the worst case, about 15 times more flops than the one you'll find in Scalapack, but actually executes faster than the one in Scalapack because it generates an arbitrary amount of concurrency and is suitable for GPU implementation. Our KBLAS library that fills in many holes in the vendor's level 2 and level 3 BLAS for GPUs and mics, including these batched and hierarchically low-rank routines. A preconditioner called balancing domain decomposition with constraints, which is very good for highly heterogeneous, high-contrast elliptic problems. It does a lot of flops on interfaces, but you don't need to align the interfaces with material properties. And so it reduces the number of outer Krylov iterations at the expense of a lot of very cheap inner flops because that data is already cached. So it's a good trade-off between work and synchronization. The fast multipole method, one of the best algorithms for exascale, if you do it exactly, you may not beat multigrid because there's high constants, but if you do it approximately, you might have a preconditioner that's better than multigrid as a preconditioner, and in fact, often this is the case. A new take on cyclic reduction, which applies hierarchical low-rank compression at each stage of the cyclic reduction to reduce order n squared complexity to order n log squared n. And a new nonlinear preconditioning called Aspen, the additive Schwartz precondition in exact Newton, that takes the global synchronization of Newton and turns most of it into some local Newton problems with an occasional global synchronization. And then an example of our high order work is NECBox, which is a derivative of the famous Gordon Bell Prize winning NEC 5000 code that uses extremely high order schemes to minimize runtime to a given accuracy. You may not need 30-second order. I'm not joking. That's one of the winning orders. But that may be the fastest runtime. You don't see the convergence rate because you don't have enough precision to actually measure the effect of 16th order versus 32nd order. But the flop intensity of the 32nd order actually wins the game. So given that I'm running out of time, I'm going to be unjust to my colleagues and not go through some of the technical details, but just flash some of these results of these 4 points of light. So this is a brief on this eigensolver. It exploits a cute factorization called the polar decomposition, where any matrix can be written as a product of a unitary matrix and a symmetric positive definite matrix. This is like R equals, e to the I theta, where this is the e to the I theta and this is the R, but generalized to many components. Once you have it in this form, there's a simple eigendecomposition for this SPD matrix that gives you the overall singular value decomposition. This is backward stable. It does a lot of flops, but it beats any of the things in Scalapack against the best implementations. This is today the fastest dense SVD on a variety of configurations. And when you taskify it, you compress, this time is from left to right here, all this dead space between subroutine calls can be compressed out with a direct acyclic graph for a final juicy speed up. And this is showing its execution on Intel Haswell's factor of 10. Haswell's complemented by K80s. And it scales very well in terms of more GPUs. The K-BLAS, this is a set of the kernel routines for dense linear algebra, in this case symmetric dense linear algebra, that are not effectively implemented on especially the level 2 BLAS. They're memory bandwidth limited in many of the vendor implementations, or they use too much memory. For example, the cuBLAS in place, where you can use half as much memory, only executes at this rate. This is performance, so up is good. This is DGEM, which is considered the best practical performance for this system. cuBLAS has an out-of-place execution, which is here, but it uses twice as much memory. Our KBLAS is in place, but tracks the performance level of the out-of-place. So this is an example of the kind of optimizations, and this is now distributed in the cuBLAS. So we're extending that to batched operations, and of course I'm going very fast here, but we're operating very close to the theoretical, the so-called roofline best for algorithms at this flop intensity, building this into a library called HICMA with a variety of pieces at different levels, addressing the bottleneck, the narrow waist of the hourglass between many applications and diverse architectures at the bottom with a common API, many applications. And getting to one that I should have gotten to earlier, this is the BDDC applied to the SPE10 benchmark. You set the condition number you want for your outer iteration. You work very hard on the preconditioner, and you get that back. You wanted a condition number of 10. It came out as 15. The number of iterations was fixed in strong scaling for a variety of these systems. Similarly, for the diffusive Maxwell for electromagnetic inversion, a complicated discretization in terms of the finite elements, very good tracking of the prescribed condition number with the resulting condition number, and number of iterations being correspondingly reduced. Reducing the number of global synchronizations with a lot of local work. The technicalities I don't have time for. It does exploit hierarchical low rankness, and the rank is a function of the accuracy you want and the tile size you use, and you can more or less, for a given problem, discover the appropriate rank size. FMM, a perfect algorithm for exascale, scales perfectly almost on the Intel Xeon Phi. Black line is perfect strong scaling. This is a combination of MPI processors and threads per processor going out to 256 for this very exascalable algorithm. So it can be used as a preconditioner, and I really have to, I didn't pace myself very well with enthusiasm of the first part of the talk, but I think we will learn, as I said earlier, to create separate threads for logically separate tasks, give them priorities, assign them on a critical path like an operating system, and join the priority threads in a DAG-like way. This is, I believe, the way that we will exploit exascale computing. And there are plenty of ideas to adapt or substitute our favorite solvers with methods that satisfy these 4 pillars. Programming models and runtimes may have to be stretched to accommodate, but everything should be on the table for trades. This is the theme of co-design in the current Department of Energy exascale project. So thank you to sponsors, and I repeat Jan's invitation to join your colleagues in a similar kind of a meeting in Athens in October. Thank you.
Let's thank our speaker. It's my job to intimidate the speakers.
That's
also,
right.
You know. But I do want to allow for a couple of questions here because you know you flew all the way from KAUST, you know, so bear with me while we get a couple of questions in. And with your permission, the slides will be posted as a PDF and available. So so we'll make sure they're available so you get to see all the details in between, because there's a lot of interesting work here. So with that, any questions? And raise your hand, and we have our microphone runner. Shout if you don't see us. Okay, there's one here. Okay.
You talked about this API, but not in depth.
No, that's correct.
And,
it's evolving.
You really need kind of an intelligent learning resources and know all the resources and the performance and the algorithms and mapping of
I fully agree. The difficulty with poly algorithms is they have a lot of tuning parameters, a lot of choices. And right now, we give very little guidance to users. Even a package like PETSI, you know, all the options can be quite overwhelming. There are defaults. They're not very efficient. And so I'm by no means suggesting that the expertise of a user within an application domain is going to be easily replaced with machine learning. Machine learning may be able to help more than we think maybe, you know, looking at it from 2017. But this is not a friendly environment. You don't just call a scale-up hack routine anymore. There'll be a lot of tuning.
It's more of a, the machine learning of the heterogeneous architectures and what runs well where and so on.
Yep. Thank you. Thank you very much.
One more there.
Yeah, Jess.
If we go into the world of quantum computing, would the way of how we adapt the algorithm change?
Well, I don't have much expertise to address quantum computing. It appears as though cryptography and unconstrained optimization are two classes of problems that quantum computing has, sort of a proven opportunity to run in. Constrained optimization, like inversion, I'm not at all sure we have a clear path to improvement from quantum computing. But it's stupid to be skeptical, right?
Well, with that, join me in thanking. So here's before you give an applause here. So Dave will be on the panel this afternoon. We have some room there, so queue up your questions. Be ready for the panel conversation. So you'll be part of that. So let's thank Dave again, and yeah.